Okay, so I guess we're gonna get started. This lecture is for pavement design, and this is the foundation of all pavement design methods. Basically, we'll follow the traffic loading approach. So we're gonna look into traffic loading analysis. Then we are gonna spend the majority of the time in equivalent single load factor, equivalent single axle load. We're going to look at the AASHTO 93 method, the TAG method for Canada. We will also look a bit into the design spectra method that is currently used by the Mechanistic Empirical Pavement Design Guide, which is the latest pavement design approach. And we're going to do some sample calculations. We're going to look at how to do a pavement design estimation of traffic loading when you have some unknown axle loads or traffic. And so the first thing that we need to know is that there are three main methods. Some of them are not used anymore. Others are still used, and others are the latest. So the fixed traffic approach, this was the way to do things some time ago. And it was based on a single wheel load. And the pavement was designed to withstand the load of a single axle. And this was mostly used for airport pavements. However, this is not utilized anymore. The fixed vehicle approach is the one that is embedded in the AASHTO 93, and this is still used today. This was used for a few decades. It has been replaced recently, a few years ago, and it typically assumes standard type of axle and applies a number of repetitions of loads through that standard axle. So basically, if you think of the traffic mix, we have many type of vehicles, but what this method does is it converts all vehicles into this standard axle, into this standard vehicle. And then by converting everything into a standard one, just apply a number of repetition to simulate how much is going to be the traffic demand. Finally, the variable traffic and variable vehicle. This method uses what is called an axle load design spectra. So it considers the different type of vehicles, different type of loads, the number of repetitions for every type of vehicle, every type of load, and every type of axle. This is the one that is used nowadays with the Mechanistic Empirical Pavement Design method, and is also used for the Portland Cement Association for rigid pavement design. This is the best approach, but requires a lot of information. It requires you to have detailed historical records of the traffic that you have been observing, and also a forecast towards the future of detailed traffic that you are expecting. How many passenger cars, how many SUVs, these are not important because, as we will see soon, the passenger cars are not damaging the pavement as much as the heavy good vehicles, the buses, the trucks. So for those, we will need to have a very good characterization. So for example, think of these two trucks we have here. The one on the top is a straight truck. It has a steering wheel on the cabin, and it has a single axle load on the back. You can see it's just one tire. And if you see the vehicle in 3 dimensions, you will see 2 tires, 1 axle, and 2 tires on the back. And the steering wheel will be just 1 tire, 1 axle, 1 tire. If you look at the truck at the bottom, this one has a steering wheel on the cabin. Then it has a tandem. The way to recognize a tandem is because you see 2 tires very close to each other. And when you look at the three-dimensional, in reality, you have two pairs of two tires very close. And the trident, which is the axle on the back, in this case is three axles, and each axle will be two tires, the axle, and two tires on the other side. We will look at this soon. So the load spectra will require you to have a detailed table like this one, where you have the number of axles of all type of vehicles you expect to use the pavement that you are designing. And this is very complicated because you don't know. You are forecasting something in the future. And for this reason, this method is not yet that utilized. And everybody tries to bring everything into the standard axle load. So we're going to spend mostly the rest of the lecture in the standard or equivalent axle load, okay? So we're going to look at what is an axle load factor. So as I was telling you, you can see there, each of these is over here, is a single axle. You can see is two tires, one axle, and two tires, okay? Now, the only thing that is changing here is the weight. So in the first case, we have 18,000 pounds or 80 kilonewtons. In the second case, we have 22,000 pounds or 100 kilonewtons. In the last case, we have 10,000 pounds or 44 kilonewtons. Now, since the 1950s, 1960s, the 18,000 pounds or 80 kilonewton axle was established as the standard axle. So everything will be converted into this axle. However, the conversion is not linear. So it is not like if you have 36,000 pounds, you will have twice as much the damage of this axle. In reality, what happens is that the relationship between the damage that is caused by the axle load and the load on the axle is nonlinear. So this nonlinear relationship, we're going to look at some equations and some tables that will provide us with the actual values, but you can see here an example. If we think of the damage produced by an 18,000 pound and we normalize that to 1, so we say the pass one time this axle with 18,000 pounds pass over a road, produce 1 unit of damage. Then the 22,000, because it's non-linear, is producing 2.2 times the damage of the 18,000 pounds. And the 10,000, which is not even half, is only producing 9% or 0.09 the amount of damage that the 18,000 pound axle is producing. So this is the nature of the relationship. And what we're going to do is everything will be expressed in the 18,000 pound axle, and we will calculate how much damage the pavement will suffer after a given number of passes. And then that number of passes will be proportional to the service life of the road, say 10, 15, 20 years. So, for example, look at these trucks we were looking before at. Imagine you have 6,000 pounds on the steering wheel and 15,000 pounds on the single axle on the back. Your 15,000 pounds will produce something like 0.48 units of damage. The unit of damage is called load equivalency factor. So this load equivalency factor is your unit of damage. You are probably wondering where I took this from, and there are tables and equations. So for now, don't worry about it. You will read this from somewhere. I just want to show you that when you look at the damage produced by the axles of a truck, you can just make a summation. So the damage produced by the steering wheel is 6,000 with 6,000 pounds is 0.01, and you can just make a summation. And the summation of the damage of the axles is called truck factor. So the truck factor is the summation of the damage of all axles of a truck. Okay? So for example, if you look at this one here, it will have 1.1 as load equivalency factor, so 1.1 units of damage. And over here, we'll have 1.1 units of damage for this one because it's the same weight. And the steering wheel will have 0.19. You make a straight summation and you get a truck factor of 239. So this truck produced 2.39 units of damage when it passed over a pavement, while this truck produced 0.49 units of damage. Is this clear? We're just trying to convert everything in units of damage. Okay, so, and that is the concept of the load equivalency factor. Now, we will take all the traffic, all the different type of loads and axles, configurations, and everything is gonna be brought into this equivalent axle load factor. And this will give us the damage by a given axle relative to the damage of the standard axle, as I have been explaining. And the standard axle is your 80 kilonewton. However, if you go to Europe use, I think it's 15,000 pounds. You can check. So, but US and Canada utilize the 18,000 pounds or 80 kilonewtons. All right. Now, the way that they took this and estimated the damage is a relationship between the number of repetitions that you need to reach the end of the service life. So if the service life of the pavement is denoted by NF, then the damage of a single pass is 1 divided over NF. At the end, when you have the total NF, then you reach a 100% damage. So the load equivalency is being expressed as the number of load repetitions that the pavement requires as compared to the standard. Now, the Asphalt Institute back in the 1960s and 70s did the calculations, and as I was telling you, is not a linear relationship between whatever is your standard axle and whatever is the load. Is a power of 3.29. So this one over here is actually the equation where you have your standard axle, so this is 18,000, and whatever is the load that you have, okay? So again, you will have a division of the load on the axle, and you will divide this over the 18,000 pounds or 80 kilonewtons. And all this is going to be raised to the power of 3.29. Okay, so earlier in the class, when I show you these values, 2.2, 0.9, they are coming from this equation over here. And the equation was estimated by considering the amount of tensile stresses and strains and the elastic modulus. And I'm not going to go into the exact demonstration of this, but this is the type of equation that was utilized. The Asphalt Institute also established one for damage based on rutting, and they established one for damage make on fatigue failure. This is due to cracking. So there are actually two types of damage that you can experience. So cracking damage and rutting damage. Okay? And when you look at that type of damage, your cracking is happening because the load of your tire is pushing the pavement down, and then you are suffering this tensile stress at the bottom of your surface, which is your hot mix asphalt surface. The cracking is happening because of this strain that is being transferring the load from the surface into the granular base and subbase. And if you look for this type of damage, you can probably find nice images of rutting. See? This one, for example, this is rutting, okay? So you see that is like if you have Play-Doh and the tires have pushed down the pavement, okay? And then, of course, this is rutting combined with cracking, because when you damage with one of them, the other one will also appear. This one will be cracking. So you don't really see the deformation from the wheel path, but you see the pavement all broken because of the cracks. Okay? So, all right. So at the end, we can approximately know that the power of 4 is sometimes used by some approaches. Others use values between 3.2 and 6. So with this equation, they produce tables like this one. So what this table is giving you is the amount of damage or equivalent axle load produced by different loads. So for example, 1,000 pounds on a single axle produce 0.00002 equivalent load factor. So this is the amount of damage that 1,000 pounds produce. So if you look for a passenger car, the weight of a passenger car is somewhere around 4,000 pounds, okay? And those 4,000 pounds will get distributed in two axles. So if 4,000 pounds, that means 2,000 pounds. When you look at 2,000 pounds in an axle, you have 0.00018. This is the damage that a passenger car will produce, approximately. The one axle of a passenger car, one pass. But when you look at a truck loaded with 18,000 pounds, that produces one. So this is really 0.018% of what a truck will do to a pavement. And that's the reason why passenger cars are typically ignored. Of course, you notice here that you have also tandem axles and tridem axles. So again, a tandem axle will be this one here on the back, and a tridem axle, I don't know if we have a tridem, we have here. This is a tridem axle, okay? Tridem, tandem, single. So the table is telling you the amount of damage of the single, tandem, and tridem axles, depending on the amount of load that you have. Okay? So now we're gonna look into the Ashton 1993 method for traffic load analysis. The first concept that we need to handle is the structural number. The structural number is basically how strong is the pavement. Oh, sorry, this typing. Okay, so this is how strong is the pavement. That is the structural number. And it has a common equation based on the thickness of the layers and some coefficients associated to it. So your H1 is the thickness of the hot mix asphalt layer. Your H2 is the thickness of your base, and your H3 is the thickness of the subbase. So for example, if we look at this first equation here, my structural number will be, let's take the lower coefficient, 0.2 times, and let's imagine our hot mix asphalt layer is maybe 5 inches. And then let's go for the base. The base, let's take the lower value, 0.08, and let's imagine the base is maybe let's say 10 inches, okay? And then the subbase, 0.06, and let's imagine is also 10 inches, okay? So when you do that, you are simply going to obtain a structural number that will be 1 plus 0.8 plus 0.6 equals 2.4, okay? So it's just a value. If you make the pavement thicker, and now your base is, maybe your subbase is 20, you will increase this one to 1.2, and your structural number will also increase, and now will be 3, okay? So that's the concept of a structural number. It's just a way to say how strong the pavement is. These coefficients come from material testing. So your coefficients, A1, A2, A3, they come from material testing. And these are the common values. These are the most common values. This is the range for the A1, which is for the hot mix asphalt. This is the range for the granular base, and this is the range for the granular subbase. There are other structural numbers in the literature. For example, the World Bank established a structural number that is a modified version of the one we just saw before. And this one used the bearing capacity of the soil. The subgrade soil is considered in these calculations. So I'm not going to make a full example, but you can see here the equation. And the equation uses the CBR values, the California bearing ratio, to estimate the bearing capacity of the soil. So depending on the bearing ratio, you can see here the values. For a value of, say, 100, your structural number will go, for the subgrade, will go to 2.1 approximately. So that means that to this value we just calculated, you will be adding the contribution of the subgrade soil. This is just a modified approach that the World Bank uses. This one on the left-hand side is our AASHTO approach. So there are tables like this one that gives you the load factor or amount of damage, but considers how strong the pavement is. So, and those are the tables that the AASHTO uses in the design method. So the pavement structural number here, 1, 2, 3, 4, 5. So for example, in this previous case, we estimated a value of 3, you see? So in that case, we will be using this value over here. And we will be reading from this column, and you will be looking at what is the amount of kilopounds that you have on the axle. So 2,000, 4,000, 6, 8. When you get to 18,000, which is here, in this case, you see your amount of damage is 1. It doesn't matter how strong the pavement is. It's 1 because this one is your standard. Okay, so now, having explained what is the load equivalency factor, we use the load equivalency factor to estimate the equivalent single axle loads, which is basically how many load repetitions the pavement can withstand. And this depends on several factors. So we will consider the average annual daily traffic. We will consider the percentage of trucks, the directional split, the load design factor, the number of years, the number of days in a year, and the growth factor. I know it's a bit complicated, but don't worry about it. We're going to make a couple examples. So maybe before I do the example, let me just explain something here. So on any road, let's imagine we have a road. Sorry, not with an arrow. So let's imagine I have a road with 2 lanes per direction. So the AADT, if you remember, is considering both directions. It gives you how many vehicles per day you have on the road in both directions. And these vehicles will include trucks. If you multiply the ADT by the truck factor, then you only have the trucks per day on both directions. Correct? Now, if you multiply the AADT by the truck factor by the directional split, then you will have the trucks per day per direction. Correct? If you multiply the AADT by the truck factor by the directional split by the low lane design factor, then you have the trucks per day on the low speed lane. And this is the basis for the estimation of the ESALs. So the ESALs, which are equivalent single axle loads, they are based on the trucks on the design lane. And the design lane is the low speed lane, which in a highway is typically this lane over here, which is where your trucks will be. I hope you have paid attention when you are driving on a highway that the trucks typically stay on the far right lane if you have multiple lanes. And the reason is because of regulations, but also because the entire facility got designed because of that reason. Okay. Then a word in terms of the growth factor. The growth factor uses this equation that you learn in, I think you learned this in project management and principles of economics or something like that. ENGR 301, you learned something like this. So this one is telling you in a given number of years, how many times in n years, how many times the traffic accumulates. Okay, now let me just spell this in a different way. This is telling you the accumulated traffic in n years, considering an annual growth of R per year. Do you remember this? I hope you do. Okay, so we can make an example. I'm not sure if there's any question, but we're going to make an example and we're going to just crunch the numbers for this. Any questions? Okay, so let's look at this example, okay? We're going to have a 4-lane highway. So this is this case, right? Where we have 4 lanes. And we're going to calculate the cumulative design traffic load in terms of equivalent single axle loads. We're going to assume a 25 years design period. So when you go here, your N, in this case, is 25 years for this example. And we're going to use a growth factor of 3% per year. So if you go back here, that means that your R is 0.03, which is a 3%. We also know that we have a lane distribution factor of 80%. So 80% of the trucks will drive on the low speed lane because of the lane distribution factor. And we also know that we have 1,500 trucks per day. And this is, of course, in both directions. So if we come here and we apply this, we're going to have 1,500 trucks. We don't know the directional split, but we're going to assume it's a 50%. And we have an 80% of lane distribution factor for the low speed lane. This will tell us that on the design lane per day, we have 1,500 by 0.5 by 0.8. So you have 600 trucks per day on the design lane. Let me just see what color do we remember. Okay, let's go for this one. All right, fine. So we know now how many trucks we have, and this is the percentages that we have for different type of trucks. So we have 2-axle trucks, 20%, 3-axle, 25%, 4-axle to 30%, 5-axle 15, 6-axle 5%, and the rest, which could be buses, garbage trucks, fire engines, and so on, 5%. Okay, so we can actually use a little Excel, and we have our traffic to axle, to axle, 3-axle, 4-axle, 5-axle, 6-axle, and the others. Okay, and we have here the percentages. So we have 0.2, 0.25, 0.3, 0.15, 0.05, 0.05. Okay. So those trucks look like this because they give us the weights from historical information. So this is my 2-axle, 3-axle, 4-axle, 5-axle, 6-axle. Now, we're gonna assume that the pavement has a strength, structural number of 5. So this is something I will have to give you, or I give you a way to calculate, okay? How do I give you that? Well, I will simply go back here and I will tell you what is the thickness of the, I will come here, I will tell you what is the thickness of the hot mix asphalt, the thickness of the sub-base and base, and I will give you the coefficients and you can calculate, okay? Or I simply tell you what is the value for our structural number. So let's just assume that is this one. So we're aiming at using this type of table, but we will be using here the structural number of 2. Now, something else I didn't mention, but that we will learn later, is called the terminal serviceability. It's called PT. So PT is terminal serviceability. For now, we're gonna ignore and you're just gonna accept the value that I'm gonna give you. Later, we will come back to this concept and I will explain what it is. So for now, we're just gonna use that value. We're gonna assume that the steering axle will produce twice. So the damage from the steering is twice the damage of a single axle. Because it's half the contact area. This is an assumption that you can always do. It's a rule of thumb assumption. Okay, so with that in mind, we're gonna convert this, our truck, in pounds or in kilonewtons, up to you. So our two-axle truck is gonna have 12.1 kilopounds and 22 kilopounds. And so we're gonna go into the table and we're gonna see how much damage this truck produce. So we need to get the truck factor for this thing. So let's see, 12,000 kilopounds. We are working here. So we are assuming we have this. And we're looking at 12,000 pounds, kilopounds. So it's here. And if that is the case, that is producing 0.189. So my two-axle truck has an axle of 12,100 or 12.1 kips. And my load equivalency factor is 0.189. Is the one I'm reading from here, okay? This one. This 0.189 is my load equivalency factor for this axle. So this axle produce 0.189 units of damage, but it's a steering wheel. So it produced twice the amount of damage. The axle on the back has 10,000. So if I go for 10,000, my 10,000 are producing 0.088. And that is a single axle. Sorry, no. It's 22,000. Sorry, guys, it's 22,000 kips. So it will produce 2.18. So my 22,000 kips produce a load equivalency factor of 2.18. So my truck factor is 218 plus 0.189. So this is my truck factor for a two-axle truck. Is this okay? Okay, let's do another one. So we have the three-axle truck. And we're going to have 12,000 kips and 40,000 kips. So my three-axle truck is going to have a steering wheel of 0.189. Sorry, because it has 12.1 kips. And then it has 40 kips. You can see it here. This is my truck, okay? So it has 12,000 kips and 40,000 kips. And when I go into the table, sorry, where's the table? Before, yeah. So when I go into the table, my 40,000, which are here, sorry, 1 second. Let me see what type of axle is this. Yeah, this is a tandem axle. It's a tandem axle. You see, it has 2 tires. It's not a single axle anymore. So we need to use the tandem axle, which is here, tandem axle. So we need to use that table. So we are again in 5 and 40. So it's 2.08. And the torque factor will be 208 plus 2 times the 0.189. Actually, here is also 2 times, right? Now, do you notice how the 3-axle truck has 40 kilopounds on the axle, on the back, produced 2 units of damage. The 2-axle truck has 22,000 and produced the same amount of damage. But the 2-axle is a single axle. This is a single. And this is a tandem, meaning you have twice as much tires. So although the weight is double, you produce the same amount of damage because you basically distribute the weight in more contact points. Anyways, so we have here the torque factor for the 2-axle. We have the torque factor for the 3-axle. And we can continue with the rest of the trucks. I'm just going to show you the calculation here. So for the 4-axle truck, the torque factor is 378.8. For the 5-axle truck, the torque factor is 3.308. For the 6-axle truck, the torque factor is 3838. So these torque factors, we are going to take them and we're going to put them here because they are basically telling us how much damage one pass of the truck produce on the pavement. That's what this means. And this is what you need to remember. Okay? So I'm just going to copy the torque factors there. So we have 2.558, 2.458, 3.788, 3.308, 3.838. And then finally, my last one has 0.65. They gave us that. So if I ask you, for these trucks, which one produce more damage to a pavement, which one would you say? I'm waiting for an answer. Maybe somebody might want to open the microphone and tell me. 6.8. I'm not sure what is 6.8. Ah, the six axles. Yes, the six axles is the one producing more the majority of the damage, followed by the four axle. Okay, correct. Right. So now, but this is only one pass of the truck. Is one pass only what we're looking at. Okay. So we need to really see how many passes we have for those trucks. So we calculated that before. So let me just go back here. And we said we have 600 trucks per day on the design lane. Okay. So you can make 600 trucks multiplied by that. And this is the amount of damage of 600 trucks per day. But I want to design this in 25 years. So I am after 25 years. Now, these 25 years, as I was explaining here, we need to get how many times is the accumulation of 25 years of damage. So I am after 25 years accumulated damage. So I am going to use this equation here. So let's try. I have 1.003, sorry, 03. That is the 1 plus r, okay? To the power of 25 years, okay? 1 plus r to n. Minus 1. And all that gets divided over r, which is 0.03. Are you guys clear with the equation? It's just that. So I'm going to put an equal so it calculates and tell us how much that is. Oh, I did something wrong. Apparently, yes, that bracket. I might have an extra bracket. Just a second. So it is 36.45, the number of times you need to multiply the traffic on the base year to get to the accumulation in 25 years. Now, this one over here is in 1 day. correct? So I still need to multiply this by how many days I have in 1 year. So let's say 365 days in 1 year, okay? And now I need to multiply by 36.45. Okay, but there's another way we can do this. So I can maybe simplify this a bit. So this is in 1 day. Sorry. And let me make here a summation. So that is the summation of the amount of damage that I have. Oh, yeah, sorry. Um, I forgot to divide this by 2 because I have this in one direction. And now I want to get this. This is, let me just insert here a bit. This is damage in 1 day from all trucks. If I multiply by 365 and by 0.5 and by 0.8, sorry, I already have just a second. I did by 600 and my 600 were already here, right? And they gave me 1,500 trucks per day in both directions. So I did by 0.5, by 0.8, that's 600 trucks on the design lane. So it's 600 trucks. Okay. Okay, yes, because I have a different calculation there. So here I don't have to divide by 2. This is the damage in 1 day, all trucks on the design lane. And now I do this by 365. So this is my damage in 1 year. You can, of course, assume that the year has less number of days. And I want to have this accumulated in 25 years. So I multiply by my factor. I forgot, delete the factor. Somebody remember how much was the factor? Was it 36 something? 36.45. Yeah. Okay. Um, um, there's a little mistake because I think I did not consider here the percentage. So this is a 20%. and I need to consider the percentages. So I forgot to multiply by the percentage here, okay? So 600 trucks total, but this is just 20%. So of this type, we have 307. This one is again 600, that's correct. The truck factor is 245, correct? And 25%, okay? This one is 600 by 3788, which is the truck factor or the amount of damage of one truck. And this is 30% of the 600, etc. So at the end, this is the damage for 25 years accumulated for all trucks. So let's put it this accumulated damage after 25 years from all trucks. And this is what we call ESALs. Okay, I'm going to stop here. Questions? Okay, I don't hear anybody. I presume there are no questions. This is your damage after 25 years because you accumulate. So the 36 is telling you how to take 1 year and accumulate that initial year that is growing at a 3% every year and make the total summation, so the accumulation in 25 years. This is what you use for the pavement design. So in the next class, this is the starting point, this value that we have here. Okay, let me just save this calculation on Excel. I will post this online, okay? Now,
Sir,
go ahead.
I just had a question. What
Yes,
does the
please.
damage represent? Like, there's 26 million damage on the lane. What does that mean?
It's just a unit of damage that is standardized. Um, and at the end, there's no physical representation. Like I can tell you that means 3 centimeters of crack. I cannot tell you that because what they did is they graduated the damage so that the pavement can withstand a certain amount of damage after a certain number of years. So the equations that I showed you before, this one, or if you want this one that is cracking and rutting, your rutting oh, what happened with the text? Yeah, so the cracking is at 20% of the surface, and that is the damage. And the rutting is half an inch, or if you want, approximately 12.7 millimeters. And this is the damage that we are having after the design life, after the ESALs on the design life. So what they did is they calibrated equations that will correlate to this amount of damage that is a imaginary unit so that it will arrive into these amounts after your design life. I know it's a bit ethereal, but that's how it works.
Okay, thank you.
Yeah. It's going to become more clear when we actually crunch the numbers. Right now, I'm just getting an output that we are going to use to design thickness in the next class. So it will be more clear in the next class. Otherwise, come back to me. But I cannot jump and bring the rest of the concepts in this class to try to further explain, because then I will make it very complicated. It's already complicated, this class, I know. Okay. So this method we just look at is the ASHTO. Remember, the foundation was this type of tables that are graduated for how strong the pavement is and how much weight you have, and what type of axle you are looking at. However, we also have another method that is in Canada, proposed by the Transportation Association of Canada. And this method is similar. It was based on a study that they did and produced equations. So instead of the table, you will look at equations. This is the equation for the load equivalency factor, or the amount of damage produced by a steering wheel. This equation is for a single axle load. And if you see, actually, the equations are almost the same, but the single axle load produces half the amount of damage as the steering wheel. The steering wheel produced 2 times, because look at the denominator. The denominator of the steering wheel is half the denominator of the single one. This is the equation for the tandem, and this is the equation for the tridem. So what this means is that instead of going and reading the values of load equivalency factor from tables, you use the equation directly. So the L is the load that you are observing. And if you plot them with different loads, this is the plots of load equivalency factor, or damage, that the different weights on the different type of axles will produce. So which axle produce more damage faster? I'm asking you, based on the graph. Remember, load equivalency factor is damage. So look at the 10 tons, for example. If you have 10 tons, you are here. Okay? If you have 10 tons and you go into your tridem, this is the amount of damage. If you go to your tandem, this is the amount of damage. If you go to your single, this is the amount of damage, about 2. If you go to a steering wheel, this is your amount of damage, about 4. So which axle produce more damage?
Steering.
Thank you, the steering. The reason is because the steering has less surface contact than a single axle. The steering has 2 tires. The single has 4 tires. The tandem has 8 tires. And the tridem has 12 tires. So the load got distributed in more contact points. Now, if we go back to the previous example, and we use exactly the same values, 25 years, 80% of the traffic on the low speed, or the lane, the design lane, 3% growth, 1,500 trucks, everything is the same percentages. And we take the loads that were given to us. So here we have 5.5 tons, 10 tons, 18 tons, 16 tons, 17 tons, metric tons, 25 tons, etc. So we will take this and we will use these equations. So in this case of this truck that we have here, okay? $5.5 will go here in my steering wheel, 5.5. So you will have 5.5 to the power of 2.9093 divided by 206.782. You have a point 689. This 10 tons as a single axle. So we'll go here in this equation, and you will have 10 to the power of 2.993, sorry, 93, divided over 413,565. So 1.96. If you go to this one, the 18 is a tandem, so you will use the tandem equation, this one over here. So you will take your 18, you put it here. So 18 will go to the power of 2.54 over 660.06. So you will have 2.33. Okay? Is this clear? So you take the loads and you plug it in directly in there. When you do that, you will estimate the load equivalency factor for every axle, and then you can add them all. This will give you truck factors at the end. It's the same approach we did before. Instead of using the table, we're using the equations. Now, look at my truck factors based on TAC. For TAC, my truck factors, maybe let's copy the. So for TAC, my truck factors, the two-axle truck is 265. Look, I had 255, so it's bigger, slightly bigger. My three-axle is 3027. My four-axle is 43848. The next one is 4.445. The next one is 4.8360. And the last one, let's keep it in 0.65. So I end up with 28 million ESALs. This is the amount of damage that the pavement will accumulate in 25 years. AASHTO was 23 million, almost 24 million. TAC is 28 million. So TAC is more conservative than AASHTO. It produced more ESALs. And because it produced more ESALs, you need a thicker pavement to withstand the load. We will see that next time. Okay, so all this information that we have seen so far, where we are given the trucks and we know what are the loads and we know what are these percentages, and we know what is the growth factor, and all these things, they come from traffic count data. And traffic count data is typically done with automatic classifiers that you will place for 1 day to 3 days. And you will typically just consider the good vehicle. So you forget about the cars. And this is what allows you to estimate your average annual daily traffic. And then also it allows you to estimate your percentage of trucks. And with the percentage of trucks, we can estimate the ESALs. When we are counting vehicles, there are different classifications. So we don't care for pavements on the motorcycles or the passenger cars or the two-axle, four-tire vehicles. These ones, we simply don't care about. And we start caring about buses, 2, 3, 4, 5, 6 axles, and so on. If you look at the Canadian classification, we don't care about the passenger cars. We will ignore them, and we will care about the trucks and the buses. And of course, there's further characterization in Canada. So you typically know, depending on the type of vehicle, so there will be names like WB19 or heavy single unit, but you will know what type of axles they have. Okay, so this is the A train, the WB20, the B train, or your buses. So from experience, we can establish what are the truck factors. So some places like Ontario, for example, they have already established what is the truck factor for different type of trucks based on what they observe on their highways. For buses as well, what is the truck factor for a bus? If it is empty or if it is full of people. Same for the truck. So there are maximum limitations in terms of the weight that you can have in the different axles. So for the single axle is 9,000 kilos or 0.9 tons. Sorry, 9 tons. For the tandem is 17 tons. For the tridem is 24 tons, etc. Now, there is an alternative method that is called traffic load analysis method. This is very similar. It does not have the segregation of the traffic. It goes directly into your trucks. So it's basically what I have explained before. There will be no differences really. So I'm just telling you in case you come across in some book, this equation is equivalent to the one we use. If you notice, the only difference is that they are using already the truck traffic. Before we use the all vehicles and we multiply by the truck factor. In many places, they have these sensors embedded on the pavement that are counting vehicles and also measuring the weight. So this that is called weight in motion is what estimates the weight for you and tells you when you have a characterization of a truck where it is given like this. These values on the axles are coming from your historical statistics on the province or the state or the country. So it's based on historical data. And that historical data gets collected by this type of devices called weight in motion. They are very accurate, and they are embedded loops in the pavement. So the vehicle will just drive, they will not perceive it, but they are being estimated the weight as they pass by. So this is an example from New Brunswick, and this is different sites where they have looked at truck traffic, and they have estimated the different factors. So this is fleet distribution, and these are truck factors as they have estimated based on what they observe on their highways. Ontario has similar, Alberta has similar sites where they have this technology, and they are calculating truck factors. So if you work or end up working for a municipality or a province or a state, try to ask for the truck factors that they have calculated in different sites where they have the weight in motion technology. And then they mix the sites to do some pavement design. There will be some guidelines how to choose depending on the type of facility and highway you are trying to design. The last method is the traffic load analysis from the Asphalt Institute. This is similar to the AASHTO 93. It uses a structural number of 5 and terminal serviceability of 2.5. And this is useful when you have no data. You have no axle load data. And you need to look for similar sites or some historical data and use some of the tables. So this will be your load. This will be the loads in kilonewtons or pounds, and this will be the type of axle, single, tandem, tridem, and this will be your load equivalency factor. So this is already pre-calculated for you. And the other thing that is pre-calculated for you is how many repetitions you are expecting of different type of axles. So here you see the third column, number of axles per 1,000 vehicles. This is based on historical observations. For every 1,000 vehicles, this is the weights that they will have. And this is the axle group and the number of repetitions. So less than 3,000 pounds, 604 out of every 1,000 will be here. Between 3,000 and 7,000 pounds, there will be 557 for every 1,000 vehicles observed. So this is just historical data that is being used. And then the load equivalency factor is also calculated based on historical data, and the equivalent axle loads are calculated by simply multiplying your load equivalency factor, the number of axles, and that's about it. This doesn't use the truck factor. It uses directly the load equivalency factor because you are dividing or breaking down the vehicles in axles. So at the beginning of the class, I told you about the third method, that is the axle spectrum. This will be an axle spectrum. You have every axle type, the weight on the axle, and the amount of damage of the axle. So if you notice, this one is only single axles. You will have something similar for tandem axles. You will know how many repetitions you have, how much weight, what damage every axle produces. You multiply the number of repetitions by the damage, number of repetitions by the damage, and you estimate the damage of every axle that you have on the mix, and then you just totalize them. In the States, there will be calculations for these values in different type of facilities. If you have highways, collectors, arterials, interstate highways, local roads, you will have the truck factors or the load equivalency factors. So I'm going to leave that example so you guys can check it out. It's similar to what we did before. Basically, you will have, in this case, a truck factor based on your statistics from here, and you will be multiplying by the number of observations. So it's the same approach as we did before. It's just based on historical data. All right. So the important thing today is that you have understood the concept of traffic load, single load factor, or damage by one pass, and then based on AASHTO or TAC, you can estimate the amount of ESALs. If you don't have historical data, then you can use these average values that the province have estimated, and you can calculate the ESALs. Any questions? We will take the ESALs and we will use them to calculate the thickness of the layers of a pavement in the following classes. And we will do it for flexible and for rigid pavements. So the ones that are based on hot mix asphalt and the ones that are based on Portland cement concrete. Okay, guys, I'm not sure if there's any question from your end. I will still go back in the next class and probably face-to-face do a quick example of ESALs and take from that point on and show you the Asphalt Institute method to design the thickness of different pavements. All right. So have a great day. I will be in person next time. Hopefully, I took a flight that opens tomorrow to Toronto. It's the first flight out of Doha. So next Tuesday, I should be there. Have a good day, guys. Goodbye for now. I will post the lecture and the recording in the Moodle, so you can watch it again if you want. Bye-bye for now.